of the physical process, biophysical process of cell addition. And all this work was done while I was a grad student at Syracuse. Now I've just moved into James Franck Institute, and where I continue to do similar work. To start, I'd just like to bring your attention to this feedback mechanism. Yeah, so feedback mechanism that involves cell addition to the extracellular matrix. So living cells actively respond to physical and geometrical cues in the extracellular matrix by forming these so-called focal additions. And once additions are formed, several chemical pathways are then functional, for example like Rho-RAC, which can feed back into the activity of the cell. And you often see remodeling of the cytoskeleton, and ultimately this feedback loop determines the emergent mechanical response or the fate or morphology of a cell. And later in my talk, I'll just talk about what happens if I add more cells into this picture. So other than cell matrix addition, you also have to deal with cell-cell addition. And we'll talk about how these two kinds of additions talk to each other. Okay. So adherent cells exert traction forces. So this was first seen by this classic experiment by Harris and Stupak in 1980s, where the layer of fibroblast cell migrate on a soft silicon gel. Okay. And what they observed was that the silicon gel spontaneously wrinkled as the cell migrated. So this sort of signal that the cell is pre-stressed that there exists. You know, this internal active stresses in the cell that exert these lateral forces that causes.
Please, microphone.
Is it not on?
Went off. Yeah, it went off somehow.
Now it's.
Did it turn on? Is it on?
It was on initially.
It was on.
And then it kicked off.
How do I turn it back?
Any experimentalist can do it.
Okay.
There you go. I'll try not to move.
Bring the microphone closer.
Oh yeah. Now it's better? Okay. Sorry for that. So what I was trying to say here that adherent cells exert traction forces, and that was seen in this 1980 experiment where you saw wrinkling of the silicon gel, and the lateral forces that cause this wrinkling is what I'm calling the traction force. Now in the past decade and a half, several experimental methods sort of evolved.
It's gone again.
It's gone again? This ring.
You have a bad karma for this microphone.
Is back on?
I'll check, I'll change
This
the
one.
battery just a minute.
I think it's going. Is the battery?
I'll just change the battery and fix that.
Thank you. Okay, audible? Right. So one of the techniques that now measure traction forces is traction force microscopy. I'll get into details, little bit of details into this later in the talk. But basically, what happens is you put a layer of beads, fluorescent beads, beneath the top layer of an fibronectin coated gel. Fibronectin is an ECM protein that makes cells adhere, and then you measure how much these embedded beads move after the cell is detached from it, and then you can solve the inverse problem of recovering stresses once you know the displacement field. There is an alternative way to measure traction forces, which is using micropillar assays. Main difference from traction force microscopy to this micropillar assays is here the response of the substrate is local because you have these elastic pillars that form your substrate, whether you have a continuous sort of interaction of the cell with the substrate here. And here traction forces are inferred from how much the micropillars bend once the cell is detached, and then you use Hooke's law basically to calculate the bending. Now we know a lot of things because experiments have been going on for the last decade and a half, And so one of the sort of visible effects of cell adhesion is the optimal spread area of a cell that cell attains in mechanical equilibrium strongly depends on the mechanical properties of the substrate. So on very soft gels, you see this more rounded morphologies of cells. These are pictures of endothelial cells taken from Paul Janvi's lab, the UPenn. And if you increase the substrate stiffness, cells are more branched and you see a larger spread area. And also this substrate stiffness obviously affects traction forces, so that you see a linear increase for softer gels, and then as the gel becomes stiffer, there is a saturation of the traction forces. So what about the distribution of the traction forces? So traction forces are mostly seen irrespective of the cell type. You always see traction forces localized at the edge of a cell. So in our own work, we saw that traction forces, even in a multicellular colony where the cells adhere very strongly, there is a strong localization at the edges. And this localization is very high at regions of high curvature. Okay. And there is a characteristic length scale here, which I'll call the traction penetration depth, is the length over which the traction stresses decay into the cell layer. Okay. Now we come to this basic elastic model of a sort of the acceptable model of a fully spread cell on a substrate. So here we are considering a stationary cell, and it forms these stable focal adhesion complexes that link the cytoskeleton with the ECM. Okay, so these focal adhesions anchor onto a fibronectin on the ECM, and it pulls on the substrate via the action of these actomycin stress fibers that exert contractile forces through the focal adhesions. And you see traction forces that point inward, and the sum over 0 for a particular cell. Okay. Now for the single cell, at mechanical equilibrium, we'll study a very simple continuum mechanical model that captures most of these experimental results. Okay. So the entire story, of course, is more complicated, but I'll try to motivate this conceptually, and I'm writing down only the relevant parts of the equation. So in mechanical equilibrium, we have this local force balance, and the cell is optimally spread. So it's a very thin, it's a thin sheet that does not experience out of plane deformations, which are more important when the cell initially spreads. Now, at mechanical equilibrium, so YA is the sort of stiffness of its focal adhesions, and U is the cellular displacement field, and U of S is the substrate displacement field. So the difference of these two times the stiffness of the focal adhesions is what the cell balances. Now, you can calculate the substrate displacement field by knowing the Green's function of the substrate, and the gradient of the stress is the traction force. Okay. Now, then we get this sort of complicated linear integral differential equation that looks like, that is solvable analytically as we have shown in our own work for specific conditions, but things get much simpler if I assume this condition that the substrate is thinner than the lateral extent of the cell. If the substrate is thinner than the lateral extent of the cell, this Green function is just a delta function. Okay, and then I can turn my non-local equation into a local force balance equation where I introduce a substrate rigidity parameter, which is basically depends on stiffness of the focal adhesion as well as the stiffness of the substrate, and these are basically two springs in parallel, in series. Okay, and as a result, and then we introduce, we'll talk about this cellular constitutive relation, which is very simple. I disregard any viscous processes at this long time scale, and this cell is anchored like a solid to the matrix, and you have compression, you have shear, and now you have, in addition, a negative pressure that comes from actomycin induced contraction. So sigma A is positive. That means the cell as a whole experiences a negative inward pressure. And in addition, we have a stress-free boundary condition, and we assume that whatever the surface tension that exists between the different phases balance out, so that you don't have any external stresses at the edges. Okay. Now, to get a feeling of what the equation does, we'll take a very simple case of a one-dimensional cell. These are relevant for elongated neuronal cells, where I can turn this local force balance equation into a closed differential equation for the stress, and I get a length scale out of the problem, which I call the penetration depth, that depends on the ratio of cellular elastic modulus B and the substrate rigidity. Okay, so on stiffer gels, what you'll see is if you solve the equation, you see a localization of the traction forces at the edges, as you saw in the experiments. Okay, and since traction is just the gradient of the stress will have a buildup at this center of the cell layer. Okay, so that's the simple physics of why you'd see a buildup of internal stresses in adherent cells. Now, in 2 dimension, of course, the situation is slightly different because there is a geometric factor you cannot ignore anymore. Now, you see that traction stresses are now, they still localize at the edges, but they're higher at regions of high curvature or whenever you have a sharp corner. So, using micropatterning tools, you can now create adhesive patterns that can effectively have any shape you want. And for example, on a square, you would see sharp localization at the corners. Now, what in the model actually tells you that you see such a localization at the regions of high curvature? For example, so if I do the force balance at the very thin strip at the edge of a cell, the cell experiences traction forces outwards. The substrate experiences traction forces inward, and then the reaction is on the cell, which is outward on the cell, on the normal to the boundary. And you also have lateral shear stresses that can induce a Laplace kind of pressure inward into the cell. And if you look at the local force balance, it will come with a factor of 1 over r, where r is the local radius of curvature. So traction forces sort of go like 1 over r. Now, at high enough curvature, you would see a saturation because of non-locality, in which this sort of simple force balance equation does not capture. So this model can actually analytically capture, for example, this spread area, dependence of the spread area on the substrate shear modulus. So you see that the cell area increases. So the solid curve is the exact analytical result from a model, and the red points are taken from Paul Janvi's lab experiments on cardiac myocytes. And we get an estimate for the contractile stress, which is about 1,000 pascals, 1,000 pascals here. And here is a sort of phase diagram of what happens to the equilibrium shape of the cell. You'd see that for very high stiffnesses, you'd see protrusions, and if you increase contractility, the overall area will reduce. Yes?
To clarify the origin of this curvature effect, your boundary condition?
No, I just said that it's because you have sort of lateral stresses. So if you take a small infinitesimal element at the edge of a cell, it experiences sort of lateral stresses and then it will induce a Laplace kind of a pressure.
You're not including a line tension effect.
No, we are not including. So if you include a line tension, then you of course get a localization at high curvature. That is just okay. So one more thing I wanted to mention before I go into multicellular cases, mechanical anisotropy of a cell, okay, is linked to shape anisotropy. Now, what I mean by mechanical anisotropy is at each point in cell, I can define the stress tensor, and I can define stress eigenvalues sigma 1 and sigma 2. Now, the stress of the stress tensor locally gives you the estimate of the local compression. Okay. And the local maximum shear is defined as a difference in magnitude of the stress eigenvalue. The mechanical anisotropy is defined here as the average of this local maximum shear. And you see that if you plot this mechanical anisotropy versus the eccentricity of the ellipse, that sort of gives you the shape and isotropy of the ellipse. You see a direct positive correlation between the two quantities, that cells which are more elongated will be mechanically more anisotropic. This is also experimentally seen in an experiment where elongated cell of the same spread area, all these cells here have the same spread area, will be more mechanically anisotropic. Now, so all this is very good because this captures the experiments pretty simply with this simple model, with the only input parameter being the contractile pressure. So what happens if we now look at multicellular aggregates? Okay, now in a simple picture, we'll have now intercellular adhesion induced by E-cadherin molecules. Okay, so now you can consider more than one cells, and each cell now adheres via this extra component which I'll call E-cadherin. The name cadherin comes from the dependence of this adhesion to the concentration of calcium in the extracellular matrix. Okay, and intercellular adhesions alleviate after you add calcium into the extracellular matrix. Now we'll see a sort of live movie as we elevate the calcium concentration over a length scale of half a day and 45 minutes. And you see that initially, starting from a very disordered arrangements, you get a nice hexagonal structure at the edge, at the junction of the cells, as the adherence junction form after calcium is elevated. So calcium, what it does is it has one primary effect. It alters the morphology of the cells. Okay, so here you see a cell pair. Okay, it almost looks like two soap bubbles merging. So you know this classic problem of a soap bubble. I'm just making an analogy here, where the interfacial line of the minimal shape of an mergent soap bubble will be straight. Okay, so you also see that for a cell, which is very nice. And so previous work in this multicellular cases have focused on cell pairs, okay, and on cell monolayers, which are consisting of 500 cells. And here for cell pairs, for example, it was argued by Chen's group that cell-cell forces depend on the size of the adherence junction, okay, the size of this junction that they form. Also in Margaret-Goddard's group, it was claimed that cell-cell forces directly correlate with cell ECM forces. Okay. And in the cell monolayers problem, you heard in the previous talk that there is a buildup of tensile stresses because of this global tug of war that exists between cell forces and cell substrate forces. What we are particularly interested in, how intercellular adhesions affect the spatial distribution of traction forces. Okay. Now, using traction force microscopy, you can calculate the substrate displacement field, from which you recover the traction stresses. And one quantity that we'll continuously use for the rest of the talk is strain energy, which is just the integral of the traction dotted with the displacement field. Now, so these are experiments done in Eric Dufresne's lab, with whom we have been collaborating for the past 2 years. So these are cell colonies, epithelial cell colonies, actually mouse skin cells, that have been grown in high calcium medium for a day. And you see a striking similarity between these pictures is that there is a localization of traction forces at the edges, regardless of the number of cells that you start with. Okay. So cohesive cell colonies appear to behave like a contractile film, as we described earlier, where so it behaves like a one single unit. As you increase the calcium, what you see is you can describe this whole colony using one material model. And so what happens in a model is, for cell colonies of sizes much less than the penetration depth, there will be strain energy throughout the cell colony. Whereas if you now look at larger cell colonies, you'd see a sharp ring at the edges. Okay, and this was seen experimentally too for cell colonies of 1 to 30 cells, and you see that for larger cell colonies there is a decay at a much smaller length scale, and then for smaller lengths, small size cells, there is a spreading of strain energy throughout the cell. Now, analytically, you can calculate something called the total traction force, defined as the total sum of the traction forces exerted by the cell. So, for very small colonies, you see that f of r scales as r cube, where r is the size of the cell you started, of the cell colony. But for large cell colonies, okay, you see a linear scaling of f of the total traction force with the size of the cell. Now, this is very interesting because the linear scaling of force with the size tells you that there exists a surface tension like quantity that actually stems from just activity, okay? And then, so Aaron plotted the total force exerted by the cell colonies for cell colonies to up to 30 cells, and there is a clear crossover from a superlinear scaling for smaller size colonies to a large cell colony, and this does not depend on the number of scales, on the number of constituent cells. And the surface tension that comes about is like 10 power minus 3 newtons per meter. That is of the same order of magnitude as estimated for other kinds of cells as well. Now, the message here which I'd like to convey is large cell colonies can be now thought of as a liquid droplet waiting a surface, where the surface tension does not come from interfacial energies, but comes from within the cell, from the active stresses that exist. Okay. Now, what happens now if we perturb the intercellular adhesion strength? What we saw till now was for cell layers that are strongly adherent. Now, if we start with a 3-cell colony from a low calcium level, and then we elevate the calcium level over the scale of a day, we see that initially we start with a hot spot at the center that sort of melts away, and then we see a nice ring forming around the cell. Okay, I'll play the movie once again. So you see, starting from a very disorganized distribution of strain energy, you see a clear sort of ring emerging at the edges. So these are time snapshots of the same movie that you saw. You see that at very low calcium level, the cells appear to act independently. So they deform the substrate independently, and you see that's why a localization at the edges of a single cell, which sort of melts away as you increase the calcium, and the cell appears to behave like a single material. Okay, and these are azimuthal averages of the strain energy over concentric contours, and you see a peak that appears at for lower times that sort of melts away as you increase time. Now, so what is the model? So the model was very obvious. So let's model the cell-cell adhesion also as an elastic spring, so that for weakly adherent cells, you have a lower stiffness of the cell-cell bond, so that the forces are not transmitted to the spring, but are transmitted to the substrate more easily. But as you stiffen the springs, it becomes a single material. Okay, and the traction forces are mostly at the edges and nothing at the cell-cell junctions. Okay, so this whole process of formation of adherence junction, okay, can be thought of as stiffening of intercellular springs. Now, these are sort of finite element calculations of starting from a three-cell colony, where we start with the low spring constant and we increase the intercellular spring constant to a very high value, and we see this experimentally obtained result. Okay, so the average strain energy can be compared one-to-one with what we saw in the experiments, and I'll stress once again. So the main message here is increasing stiffness of cell-cell springs amounts to increasing the concentration of calcium in the extracellular matrix. So that was my last slide. I'd just like to add some conclusive remarks. So the elastic model of an adherent cell, of course, there are viscous processes that you can't neglect as the cells spread, and focal adhesions continuously remodel size. The cytoskeleton also is not a solid at all times, but the elastic model teaches us few things. One is build-up of tensile stresses at the cell center, localization of traction forces, and the dependence of the traction forces on mechanical and geometrical properties of the cell. Now, strongly cohesive cell colonies appear to act like liquid drops that wet the substrate underneath by this effective surface tension that comes from the intercellular activity. And these cadherin-based adhesions, like this adherence junction, organize cell matrix traction forces to the cell edges of an adherent cell colony. Okay, that'll be all.
Questions?
How do you define the total traction force?
So you at each point in the cell, whatever you can calculate the traction stress, take the magnitude of the stress, and then integrate over the cell area.
Is that the total force exerted by the substrate on the cell?
Yes.
That should be zero, no?
No. So this is the magnitude.
Oh, yeah.
So if you of course integrate, it will be zero. So you take the magnitude of the stress and then integrate over the cell. This is not a very well-defined quantity. So the best thing to do probably is to take moments of traction forces.
Could you explain what was done in the 3-cell simulation that you showed? What were the initial conditions and how they evolved?
Oh, this is this is just a finite element modeling. So you start with a cell, so the of a hexagonal shaped cell colony, and then you solve the continuum equations and look at the
Is there motion of calcium in this?
Oh no. So the entire thing about motion is sort of not included here. So what we the model is that increasing calcium concentration amounts to stiffening of the intercellular springs. So these are three different finite element
So this is not an evolution of any.
No. This is not an
Sorry.
evolution.
All right.
This is the equilibrium for three different.
But can you tell, just qualitatively, what would change if the cells are moving?
So what would change if the cells are moving is, of course, in the context of sort of spatial distribution of traction forces, you can see a more disorganized distribution. So you can also find traction forces much deeper into the cell layer instead of localizing so strongly at the edges. And this was in fact seen in Tephard's experiment, where there is a greater penetration of traction because now the focal adhesions are continuously remodeling, and the system is not elastic, the intercellular cytoskeleton, when the cell is moving.
Okay. I should notice maybe this was just an artifact of your images,
Sorry?
but it seems to me as if when you formed the colonies, that the traction stress was lower at the boundaries than in individual cells. Is that the case, or
In the experimental case?
the experimental data?
At the cell junctions?
Yes. So I mean, before you.
Oh yeah.
Yes.
Oh, okay.
So do you have is that representative or?
Yeah.
That
It represents the experimental condition, but in the model, there is a conservation of total strain energy that is not seen experimentally. So experimental, there is some loss of traction forces to the matrix because also cells secrete a lot of things, and some amount of material is lost. So, good point.
No questions? Thanks, speakers again.